Hi, students. We're looking at section 4.7. It's me, Mrs. Pinto, and hopefully you can see these beautiful definitions that we've got going on here. So I'm looking first here at this box, and this is the most important thing that we're going to need to memorize and kind of understand. So looking at it right away, I see that the A is the base, and that's the number or variable that's going to be inside the radical, and it has an exponent. So on this side, we've got a fraction exponent, and what we can see is that's equivalent to a radical expression. And so the number in the bottom is the root, and that goes in the pocket of the radical. And then if there's a numerator, m, it would be just the exponent on the base inside the radical. And so these are called rational exponents because rational is the mathy word for fraction. So a synonym would be fractional exponents. And we're seeing here that fractional exponents and radicals are two equivalent things. It's just written in a different form. It's kind of like translating. So we can think of it as a radical and simultaneously, hopefully, think of it as a rational exponent. So let's do a little practice converting between the two. And we're first going to examine the most common. So looking here in A, at example A, we've got that x to the 1/2 power is equal to the square root of x. And what we notice there is that the denominator is 2. 2 is going to be the smallest denominator possible for a rational exponent because imagine x to the 1/1 power. Hello, that's not going to work out. That's just going to be x to the first power, and that's no longer going to need that radical. That's just a regular x. So thinking here, this is an important piece of information to remember. Then when we go to B, we'll notice if there is a base, 9, or any other number that is also square, we'll be able to evaluate them. So we think, oh, the square root of 9 is 3. So 9 to the 1/2 power. In our mind, we do this work. The answer is 3. And then if there's a more interesting fractional exponent that's not just 1/2, like 2/3, we're going to be converting it where the denominator 3 goes in the pocket. And then the numerator, if there is a number that's not 1, it will be the exponent on the base. So let's take a look at doing some conversions in our first examples here. So we want to write the expression in radical form. So for number 1, we'll start. I see that the base is x. So I know that it's going to be in radical form. The base is x, so that's the number that goes inside. Then the denominator of the fraction is 5, that goes in the pocket. This is saying the 5th root, and the exponent of 2, so it's the 5th root of x squared. That's it. On the next one, we're going to do the same thing. So it's a radical expression because it's a fractional exponent. The base is a, the denominator of the fraction is 4, and the power is 7. So I've written it in radical form. Looking at number 2, though, I see that it is not simplified. So let's go ahead and simplify that. The way that I know that it's not simplified is 7 is bigger than 4, and we see that in the original fraction. So if you're really good with fractions, I could think of this as a, and then instead of an improper fraction, I'm going to think of it as a mixed number. So that's going to be 1 3/4. And so this is really going to become a to the first power times the 3/4 is also an exponent, the 4th root of a to the 3rd. So this is one way to deal with it. Now, if I'm thinking of it by simplifying the inside in the way that we've looked at it in the past, what I'm going to do there is break it down. So I'm going to say, okay, a to the 7th is the same as a to the 4th times a to the 3rd because we add exponents. And so when I have the 4th root of this, we see that the a to the fourth power and the fourth root cancel out. So that's going to be a. And then you do see that we still have the fourth root of a to the third left over. So you can see how these could get really complicated. But for now, let's just practice continuing to translate it and then evaluate it. So looking at number 3, I see that that base is a number. So in my mind, I know that 64 is 8 times 8. It's 8 squared. But that's not helpful because what is our denominator of the fractional exponent? It's not a 2, it's a 3. So I also think, oh, 64 is 4 to the third power. I could also think of 64 as 2 to the sixth power. So we want to have all of this knowledge in our back pocket. So first of all, I'm going to rewrite it as the third root of 64. And then I'm going to rewrite 64 as 4 to the third power. The third root of 4 to the third power. And now very visually, we see that the third power and the third root cancel out. So our final answer is just 4. Pretty cool. So we have to know, okay, exponents and radicals are opposites because the radical is just the denominator of the fraction. That's how they cancel each other out. All right, 4, we're looking easier here. This one is just the square root of x. The denominator is 2. The exponent is 1, and so that's why it's just best to write it as radical x. Okay, cool. I'm going to clear out these previous drawings and zoom in on 5 and 6 because they both have a negative exponent. And if you don't remember, negative exponents just mean the answer is in the bottom of the fraction. And so like I see x divided by x squared, you ask yourself, where are there more x's in the denominator? So intrinsically, we know that this is 1 over x, hopefully. But then I'm just going to remind you that the exponent rules would be x. So this is to the first power. So it's 1. And then the rule of subtraction, so minus 2, which I think you know is equal to x to the negative 1 power. So when we've got the negative 1 power, it just means that x is in the bottom of the fraction. So this here means that this is in the bottom of the fraction. So I'm going to convert it to fraction right away. Once I move it to the bottom, it's no longer a negative fraction. Now I've performed the operation of being a negative exponent. So now I'm going to convert. So now I'm going to think of this as 1 over 1/2 is just regular square root of 49. And yay, the square root of 49 has a simple answer of 7. So this is our final answer for number 5. So here we're doing the same thing with number 6. But I see that number 6 is already a fraction. So I'll show the work for this, and then you'll be able to see how to do the shortcut. So we'll start by saying, oh, this means that the negative exponent tells us that we are going to be in the denominator of the fraction. So starting there, that's going to be 1 over 1/8 to the 1/3 power. Now the exponent is no longer negative because I've moved it to the bottom of the fraction. Well, this is like one of those complex fractions we saw in section 4.2. This means 1, this is the same as 1, oops, 1 divided by 1/8 to the 1/3 power. So let's evaluate 1/8 to the 1/3 power now, okay? Since it's kind of messy and yucky right here. So we have to evaluate exponents before we do multiplication and division. So I'm going to evaluate it. I'm going to give that 1/3 power to both the numerator and the denominator. So going back on what I said, this is what I'm going to do next. So This is coming over here, 1 over the third root of 1 divided by the third root of 8. Okay, so I have given out or distributed the exponent to both the top and the bottom of the fraction. And that's going to give me 1 over the third root of 1 is just 1. The third root of 8 is 2. Okay, so we're seeing it again. Like the stamp better for drawing my arrows. So what we're seeing is now 1 divided by 1/2. Okay, very cool. Now this means that we're going to multiply by the reciprocal. So this is 1 times 2 over 1. And now you're seeing it. This is just 1 times 2, which is 2. So a shortcut could be when we see that we have an expression like this, where there's a negative exponent and it applies to a fraction, something I could do first would change it to 8 over 1 to the 1/3. This tells me I've changed it to the reciprocal, which we see we needed to use right here in this later step. But all I did was evaluate the negative part of the exponent. And evaluating the negative part of the exponent just flips the fraction upside down. And then it would have been a lot faster to evaluate this as, oh, that's just 8. So the third root of 8, and then I get 2. That would have been significantly fewer steps. And now we can see why that's allowed. And we want to understand what we're doing so that we will make good mathematical choices. Very cool. That one was a lot of fun. Let's keep going. We're writing these expressions in exponential form, so that will be pretty straightforward. The base is z. And then the denominator is the number in the pocket, so 3. The numerator is the exponent. So in this expression here, yes, 32 to the 1/6 power is not wrong, but it's not technically in exponential form because 32 could be written with exponents. So 32 is the same as 2 times 16, which is 2 times 8, which hopefully you know is 2 to the 3rd power. So altogether, 2 to the 3, 4, 5. 32 is equal to 2 to the 5th. And so instead of writing it like this, I'm going to write 2 to the 5th to the 1/6. And here we have the exponent multiplication rule. And so this is just 2 to the 5/6 power. So if you thought of 2 to the 5th right away in step 1, we want to be thinking of equivalent exponent statements. I'll make these a lot easier since we're really just dealing with exponent rules here. Okay, 10 through 14. Now we're going to evaluate all of these. So we're going to be looking for a simplified number answer. So the idea is all of these should be able to simplify if we write them in exponential form first. So 25, instead of going and translating that, I'm going to rewrite 25 with its base power. 25 is 5 squared. So 5 squared, still to the 3/2. And now I use the power to power rule, which means I multiply the exponents. So I've got 5 to the 2 times 3 is 6 over 2, which you know is 5 to the 3rd power. And that's still in exponential form. I need to evaluate that as the numerical answer, 125. Let's do number 11 the same way. So first, starting by translating 27 to exponents, I rewrite that as 3 to the 3rd power. This is still to the 2/3. Now I think of it as 3 over 1 so that I can correctly multiply. You might be able to cross cancel, and if you can, then this will go even faster for you. So this is now going to become 3 to the 6 over 3. Well, 6 over 3 is 2. So this becomes 3 squared. The numerical answer for that is 9. Okay, looking at number 3, I see the negative, but it's not a negative exponent, which just means that the base was negative. And so for the base to be negative, this was an odd power. So I'm going to rewrite this as 4 to the, oh, I said 4. I meant negative 4 to the third power. And I'm keeping the negative there, and then I'm adding in this bracket because I want the negative to be captured with that. I'm so annoying. So then we've got to the 2/3. So hopefully you're seeing here, oh, the 3's are going to cancel. This is just going to be negative 4 squared. And negative 4 squared is going to become positive. 2 negatives make a positive. So this is going to become the numerical 16. Super fun. So it's cool. It goes from something kind of yucky to something very elegant. So yay, look at number 14. I'm going to clear out my drawings to give this one lots of space. And we see that on 14, we've got, oh, I missed number 12. So we're going to do number 12 first. Okay, going back to number 12, we're going to think, okay, that one has a negative, and then it's going to be 4 squared. And then this one is to the 3/2. So dang it. So this one here is not in the exponent, in the parentheses, like we saw in number 13. And that means that the negative is technically on the outside of the exponents. So no matter what, my answer is going to be negative here. Because according to the operations, we evaluate exponents first. So see how I've written this? This is really -1 times 16 to the 3/2, even though it doesn't look that way. So very cool. I'm going to be able to evaluate this. The 2's cancel, and I have 4 to the 3/1, which is 3. And so I've got negative, whoops, I meant to be my negative, and then it's 4 to the 3rd, which is negative 64. All right. So then here on 14, this is where we see the negative exponent. So remember, we can switch to writing this with the reciprocal right away. So that's what I'm going to do first. 25 in the numerator, 64 in the denominator. Now it's just 1/2, no longer negative. Woo, woo, woo. Yeah, I love it. So then moving on here, now I'm going to distribute both of them to their radicals. So it's going to be radical 25 over radical 64, because in this case, 1/2 power just means square root, and it's easier to write it that way. And then that's going to be 5 over 8. That one was great. So super fun. Now that I know that the negative means with a fraction, I can flip it. This one became a lot better and easier. All right, 15, 16 and 17, and then we've got a few more. So we've got some space for these. It says it says write all radicals as exponentials, then apply the rules for rational exponents. Leave answers in exponential form. Okay. So in Z, I'm just going to rewrite this in exponential form. The denominator is 3, the numerator is 2. That's all there is to it. There's nothing to simplify there because the numerator is smaller than the denominator. For 16, again, I'm thinking that as 32 is 2 to the 5th power. And then that's in the 6th root. So this is going to be 2 to the 5/6. Oh, I forgot the fraction. Okay. On number 17, I'm going to rewrite it as C to the -5/4. And then I'm going to evaluate that. So, this one is not fun. Let's take care of the negative first. So this is 1 over C to the 5/4. And no, man, 5/4. 5/4. 5/4. The 5 is bigger. So let's consider this as 1 over, which way do we want to do it? C to the 1 1/4 power. 5 over 4 is 1 1/4. So there's one whole and then there's 1/4 left over, which means c to the first power times c to the 1/4 power. Very clever. So the 1/4 power, that's going to go back into radical form. Fourth root, c to the first power. And then I'm checking out, let's see. This is a rational, like a radical in the denominator. And so remember, we have to rationalize the denominator oftentimes. So I think this is going to be a little bit tricky. Let's take a look. Checking them out. Yep. So this is becoming really challenging. I can't leave a radical expression like I have here in the denominator and it be in proper form. So I'm thinking to myself, okay, I've got 1/4. I need that to become 4/4 so that it cancels out. So I've got 1 over c, and then I have the 4th root of c to the first power. I am going to choose to multiply this by a 4th root so that they can be combined. And I need 4 as the exponent total. I have 1, so I'm missing 3. So I need c to the 3rd power. This gives me 4 and 3. I've got c, just like before. And then I've got the 4th root of c to the 4th power, which is going to cancel out and give me another c to the 1st power. The numerator hasn't changed. It's still just 4th root of c to the 3rd power because I multiplied it by 1. So the numerator is 4th root of c to the 3rd power over c to the 2nd power. First power and first power combined. Dang! I thought that would be so easy when I looked at it, but because the 5 was larger, we had to evaluate it. Because it was in the denominator, we had to rationalize it. So this really special rule here, we want to pay attention to this. We need the exponent and the base to cancel out like we saw when we did this work right here. So we need to consider and we need to figure out how many more we need so that it will cancel out with the root. So let's take a look. Let's see if we have a few more of those. Yes. In 18, we're going to have another example of that. So first of all, in 18, I don't have them in the same radical. So we're seeing, okay, I've got x to the 1/2 and I've got x to the 1/4. So if I'm thinking of these just exponent rules and I want to simplify them, they're not going to be able to be combined because they don't have the same fraction. And as you know, we can only add and subtract fractions that have the same denominator. So I'm going to change the 1/2 to 2 over 4. So this is going to be now x to the 2 over 4 times x to the 1 over 4. That's going to make my work easier. So I'm not in radical form, but I'm still thinking the same way. I've got this is the 4th root of x to the 1st power. So just like we had before with the c's, we have 1, we need 4, right? We need 4, we have 1, so we need 3 more. So I'm going to multiply this by, and I'm going to leave it in fraction form. X to the 3/4 is what I need. And I'm multiplying top and bottom by x to the 3/4. Okay, so now I'm going to be able to combine in the numerator. I'm going to add the exponent. And in the denominator, I'm going to add the exponent and I'm going to get x to the first power. It's going to be 4 divided by 4. So 2 plus 3 is 5, 5 over 4 for the numerator. One more step, we want to put it in radical form. So again, we know that 5 over 4 from our previous problem is 1 1/4. So this is going to be x to the first power times the 4th root of x to the first power, all divided by x. Oh, cool. I notice a monomial that can be simplified. And here, these will cancel out, giving me my final answer, which is a big surprise to me, of just the 4th root of x to the first power. Okay, could I have done that sooner? Yes. Did I have to do all this work? No. Looking back at it, I could have done subtraction right away. Bonehead. Okay, so I could have done x to the 1/2 minus 1/4. Oh, that would have been so much easier, but I wasn't thinking clearly. Okay, so that's going to be, just like I did, x to the 2/4 minus 1/4, which we see is going to be x to the 1/4. Okay. Oh, Ms. Tinto, you did all that extra work. Well, I guess there are many paths to the right answer. I always am looking for the speediest path. So that's why I was kind of disappointed by my bonehead mistake there. All right, cool. Let me see if I can maybe do a simplified version for 19 and kind of be strategic. We're always learning, and so we want to learn from our mistakes. So here I have definitely 2 different radicands. The base here, right? The index is 2, and the index here is 3. So I've got 2 to the 1/2 times 2 to the 1/3. And so I want to do 2 to the 1/2. It's timesing, so we add exponents. But these don't have the same base, so we're just going to convert those both to the denominator of 6, which is going to be 2 to the 3/6 plus 1/3 is 2/6, which altogether is 2 to the 5/6, which in radical form is the 6th root of 2 to the 5th, which, oh my God, how many times have we seen that? This is the 6th root of 32. This must be one of our favorite problems as Algebra 2 teachers. All right, 19 was better than 18. Finalmente, looking at 20, right here, we've got a really interesting problem. So you're like, oh no, it's 49 and 7. They're not the same base. Yes, they are. Let's start by rewriting this as 7 to the 2nd power. You're like, oh, now they're the same base. So again, this is going to be that division. I want to just do the subtraction rule. I don't want to do all that crazy radical stuff. So this is going to be 7 to the 2/5 divided by 7 to the 1/2. So that means, like we saw before, we just want to use the subtraction rule. It really speeds things up. So I've got 7 to the 2/5 minus 1/2. Aha, now I know that the common denominator is going to be 10. So I'm thinking, okay, 7, 2, okay, 10. So timesing by top and bottom by 2/2. That would be 4/10 minus 5/10. So I get a negative. This is going to be 7 to the negative 1/10. Which is going to be more work. All right, so I've got the negative. So this is 1 over. The 10 is in the denominator, so that's the index, and I've got 7 to the 1st power. So I need 10. I have 1. I'm missing 9. So now I have to rationalize my denominator, multiplying by top and bottom by the 10th root of 7 to the 9th power. 10th root of 7 to the 9th power. This is the one that I'm adding in. I had to come up with this one on my own. Now I get my final answer of, and in dark blue, the 10th root of 7 to the 9th power. This would be 7 to the 10th power of 10. The 10s cancel out. It's just a 7 here. And this is my final answer. And I have a calculator, so I can multiply that out and see what it would be. Seven to the 9th power. It's enormous. Okay, this is the 10th root of 40,000. Nope, 40,353,607 over 7. I thought it was going to be easy. All right, we did a great job. Do we have a few more to go through? Yes, we do. So now, yay, just the last 3. So now we're going to write these in simplest root and exponential form. Okay. So looking at number 21, I'm just going to evaluate this with my exponent rules to start. So remembering that it's a power to a power, I'm going to multiply 1/2 to everything, giving me 3/2 y to the 7 over 2, and then z to the 4. So now I'm going to consider these as my improper numbers. This is going to be x to the 1 and 1/2. This is y to the 3 and 1/2. And you know that this is just e to the 4th. So now I'm going to separate these, the 3 and the 1 and the 4. These are all the whole numbers. So these ones are going to come out. X to the 1st, y to the 3rd, z to the 4th. And then the fractional parts are going to stay behind. So that would be this orange 1/2 and the 1/2 on x. And so that's going to be the square root, x to the 1st power, y to the 1st power, because they both have the numerator of 1. So altogether, this is our final answer. And then this is your exponential form. So the exponential form was really easy to find. We just multiplied the exponents. And then we reduced the fraction 8 over 2 in our heads. And then the exponential form to radical form, we reduced the fractions to mixed numbers, took the whole number parts outside, and left the fractional parts inside the radical. Looking at 22. Oh, cool. So we've got a combination of skills to do here. Looking at this first one, we are going to evaluate by distributing, but I'm thinking 8 is 2 to the 3rd power. So when I distribute the 1/3 there, that's going to just become 2 to the 1st power. I'm going to have x to the 5 over 3. And then this 2 doesn't have any special exponents out here, so nothing is happening to it. It's also going to be times by 2 to the 1st power and x to the 5 over 3. So before I simplify these radicals, I'm going to combine everything. And so I know that 2 times 2 is 4. And I've got x to the 5 over 3 times x to the 5 over 3, so I'm adding 5 over 3. They have the same denominator, so it's going to be 10 over 3. Now I'm going to convert that to the mixed number. So I've got 4 x to the 3 and 1/3. So just like I did in the previous, I'm going to capture the parts that come out. This is a whole number, and then this doesn't have any fractional exponents, so that comes out. So it's going to be 4 x to the 3rd power. And then this fractional part belongs to the x, so that's the 3rd root of x to the 1st power. And this is our final answer. So we took care of the outer exponents first, then we multiplied. And when we multiplied, since we had similar bases, we added our exponents. Then we converted to the mixed number. We took the whole number parts to the outside, and the fractional parts were left in radical form. In terms of exponential form is shown right here for x to the 10 over 3. That's the exponential form. Our last problem of the day. Okay, very cool. So I see that there's an exponent on the outside. So again, I'm going to be thinking of this 125 as negative 5 to the third power. I think I'd like to combine these together. So this is fourth power, and this is 1/2 power. So this is 4 and 1/2. Oh no, 4 and 1/2. I'm going to convert that. So x to the 4 and 1/2. I'm going to convert that to x to the 4 times 2 plus 1, 9 over 2. Okay, okay. So I've got negative 5 to the third power, and then times x to the 9 over 2 to the 2/3. So how did I know to do that? Well, I always simplify inside the parentheses first. And since there were 2 x's on the inside here, I would love to combine those before I distribute and multiply. That way I do less multiplication. And so I converted it to the exponent form, and then I added the exponents, and seeing that it was a mixed number, I converted it to the improper fraction because it's easier to do multiplication with fractions when it's an improper fraction. So now I'm going to distribute the exponent. So it's going to be negative 5 to the, oh, the 3's will cancel out. So this is just to the 2 power. And then I have x of 2/3 here. The 2's cancel out, and the 9 divided by 3 becomes a 3. So x to the third power. So I guess this here would be exponential form. And then rewriting this into a slightly more simplified, negative 5 squared is positive 25, x to the third power. So I obviously prefer an elegant answer like this where there are no radicals left over. So this one was a lot of fun. And that's it for our notes today. I know that that was a lot of very interesting math work. So consider yourself a puzzle figure outer, and you can see there's times when I didn't make the best choice, and yet I was still able to get to the answer. So sometimes they'll take longer than we expect. Maybe we missed a shortcut, but there are many paths to the right answer. And so just don't give up and keep trying. See you guys in class.